Okay, good day, everyone. This is Engineer Lloyd Stampa, and I will be discussing to you fundamentals of electronics 1, and we're going to discuss today all all concepts and all theories, characteristics, discussing about capacitors and inductors. Okay, so capacitors and inductors. So let's start. We start with first with capacitors. No, as you can see here in the picture, you see these are an example of a capacitor, and this is a capacitor being discharged by a screwdriver. Okay, now capacitors are well known of storing charges like small or large values of charges within themselves. So when handling them, we should always be very careful. So as a safety protocol, if you are holding a capacitor by your hands, do not hold it directly. First and foremost, discharge it first using a screwdriver, no, in order to release all the charges. So if in case that your hands accidentally touches these terminals, at least the charge will not be discharged to you. At least you will not be electrocuted. Okay. So as what they say, in this picture, you can see a hand and a symbol for charge. So these charges are being stored and discharged by capacitors. So proceeding, as you can see in this picture here, we have several kinds of capacitors because capacitors, there are electrolytic capacitors, those capacitors that have a positive and negative terminal. There are ceramic capacitors, there are mica capacitor, mylar capacitors. They also have letters, numbers written into them, signifying their values and the manufacturers that manufactured them as products. Now, capacitors are electronic devices that are capable of storing charges, but their main function, no, their main function is to actually resist any change in voltage. Resist any change in voltage. That's the, if ever you will be asked, okay, what is the main function of a capacitor? You should always answer that a capacitor resists any change in voltage. And then the side effect, because of resisting any change in voltage, the side effect is that it can either charge or discharge. And what do you mean by charge and discharge? So since it resists any change in voltage in any given circuit, so if there is an oversupply of voltage, the capacitor charges it, those extra voltages. The capacitor absorbs all of those extra charges in itself, no, in order to maintain the voltage level of the circuit. But if there is an deficiency or an undersupply of voltage, the capacitor automatically sends this and discharges the charges within itself in order to supply the charge to the circuit. No, so if there is an oversupply, the capacitor absorbs it. But if there is an undersupply, the capacitor discharges in order to provide the extra needed charges. So again, all of the purpose of resisting any change in voltage in any given circuit. So here are the schematic symbols for capacitors. We have the fixed capacitors and we have the variable capacitors. So the fixed capacitors, as you can see here, we have this polarized capacitors. As you can see in this picture, uh, the positive sign indicates that this is the positive terminal, and those without the positive sign is automatically considered as the negative terminal. Sometimes there's no positive sign. If you can see like a white rectangle in any schematic diagram or in any electronic or electrical circuit, obviously that is the positive terminal, and the black one is the negative terminal. So sometimes you also see that in using designations for capacitors, they use rectangles, two rectangles, or a straight line and a curve. No, that straight line is the positive terminal, and the curved one is the negative terminal for the fixed capacitors. For variable capacitors, with the name alone, variable, it means that it is capable of adjusting its capacitance, whether the capacitance can increase or can decrease. So these are called variable capacitors, and sometimes based on application, they are sometimes called preset or trimmer. This letter, instead of using an arrow symbolizing variability, they replace the arrow with a letter T, no, symbolizing the word for trimmer. No, and then when you say the word gang, no, it means that if this capacitor is adjusting its value or it's adjusting its capacitance, it since it is being ganged to another capacitor, automatically the adjustment also happens to the other capacitor. Why? So because they are ganged, no? Just like how gangs work, no? If one moves, the other also moves. So if this capacitor adjusts itself, adjusts its capacitance, whether decrease or increase, obviously the other one being ganged to it will also increase or decrease depending on the what is being adjusted with the first capacitor, no? So that is the concept of gang in variable capacitors. Okay, so these are oftentimes the symbols we might encounter when we analyze circuits, whether electronic or electrical circuits. These are the schematic symbols for capacitors. Okay, now let's proceed. As you can see here in the illustration, the concept of a capacitor is that it is composed of two conducting plates separated by a dielectric material. And this dielectric material should be an insulator, no? The conducting plate should be conductor, and then the dielectric material should be an insulator. Okay, so with this setup, they are capable of storing charge, no? Q. The symbol letter for Q, letter for charge is Q. And we have this formula here, Q equals CV. That means charge is equal to C, capacitance times voltage. And one coulomb or coulomb is the unit for charge is equal to 6.242 times 10 to the 18 electrons. Okay, and we can also encounter this formula in solving capacitance. Capacitance is equal to E. E here is a permittivity constant, area of the plates times area of the plates over the distance between the plates. No, so capacitance is permittivity constant times area of the plates divided by distance between the plates. I think you might have encountered this already in your physics subjects, no, or basic electrical subjects also. So again, E here, or the E is the permittivity constant in the formula. So the unit for capacitance is called farad, and the capacitance C for conventional capacitors increases, no? As you look in this formula, the capacitance C for conventional capacitors increases with area of the electrodes and with permittivity of the dielectric material, and decreases with the distance D. No, it's very obvious because D is inversely proportional to C. So the capacitance is therefore greatest in devices made from materials with a high permittivity, large plate area, and small distance between them. So with these statements in red, you can always refer this back to this formula in solving the value of the capacitance. Okay? So the capacitor will charge up to the battery's value and will only discharge if the battery is removed from the circuit. So this statement is talking about this illustration. Like if we are going to search in the internet like how capacitors work, like for example, this is the battery and the capacitor is connected in parallel. So this capacitor will charge up to the battery's value and will only discharge if the battery is removed from the circuit. So this is what will happen, no? If you charge the capacitor based on the value of the battery, and then you will put a bulb, no? If you put the bulb, when you remove this battery, suddenly the capacitor will supply its charge to the bulb. Again, because the primary function of a capacitor is to resist any change in voltage. Now, so this is the formula, charge. This is the Q, the charge inside the capacitor. Let's say V is the voltage supply and C is the capacitance. So we have this formula C equals Q over V, or if we are going to solve for the value of work or the energy, it's equal to 1/2 times C V squared. No? So if you're going to use this equation, if you're going to solve for the work done inside the capacitor. Okay, so let's proceed. So during early times, the capacitor is known as condenser. Okay, so this is just a trivia when we go back to the history of capacitors. Capacitors are not automatically known as capacitors, but previously they are known as condensers. Okay, so you might encounter this as a question when you take the electrical or electronics board exam. The very first name of capacitors are condensers. Okay, so we now meet Ewald George von Kleist. No, it's a German scientist known to have invented the very first capacitor in November 1745. No, but we also have Peter van Moschenbroek. No, he's a Dutch professor who invented the Leyden jar. No, the very first capacitor. No, so these are two very notable scientists and professors who have marked themselves in the history of creating the capacitors in its very origin. Okay, so the Leyden jar or the very first capacitor. This is how the very first capacitor looks like. No, this is Moschenbroek creating the Leyden jar, and let's see how this Leyden jar works. Leyden jar, these are the components. It has a metal rod, a non-conductive top inside a glass jar, in which the metal rod has a chain of wire, no, and then inside the bottle there's an external metal coating and internal metal coating. No, this serves as the conducting plates. No, and with that, the glass acted as the dielectric. No, as I've discussed earlier, the dielectric should always be an insulator, and glass is obviously a very good example of an insulator. No, now although it was thought at that time that water was the key ingredient, but they discovered later on that the water is not the key ingredient. No, there was a metal wire or chain driven through a cork in the top of the jar. So you can see that in this illustration. Then the chain was then hooked to something that would deliver a charge, most likely a hand crank static generator. So you do hand cranking and then spark is created. Once delivered, the jar would hold two equal but opposite charges in equilibrium until they were connected with a wire, producing a slight spark or shock. So this spark is what you call discharging the charges inside the capacitor. So again, this is the Leyden jar, the very first capacitor. Okay, so we now have Benjamin Franklin, an American scientist. So after the creation or the invention of the Leyden jar, Benjamin Franklin worked with it in his experiments with electricity. And he also invented his very own version of capacitor, no, called the flat capacitor or the Franklin square. Nice. So if you're interested about it, you might research it further, no, in the internet about what is this flat capacitor or this Franklin square. Now, we now proceed with Michael Faraday, an English chemist. No, he pioneered the very first practical applications for the capacitors by storing unused electrons from his experiments using large oil barrels. Now, with Michael Faraday's experiments, extensive study about capacitors, especially its very first practical applications, the history used his family name Farad from the family name Faraday, so that that's why the unit for capacitance is farad, from the name of Michael Faraday. No, so farad. No, so we should always be thankful for the efforts and experiments of Michael Faraday, that we understand and know how to use these capacitors, no, in the field of electronics engineering and electrical engineering. Okay, so we now proceed with the time chronological order of the improvement of the creations of the capacitors. So from 1745, it's the Leyden jar. In 1850, the mica capacitor was invented. In 1900s, the paper and ceramic. Then in 1960, the film and foil. 1970, the electrolytic capacitors now came to the industry. In 1990, we now have the metallized film. In 1998, the field tunable film. 1999, the multi-layer capacitor. In the year 2000, we now have the ultra capacitors. In 2002, we now have the nano dielectrics. And in 2004, we now have the nonlinear composites. So as you can see, no, ever since the beginning of 1745 until now, there was this aggressive modification, aggressive invention of several types of capacitor, signifying that these electrical components or electronic components have many significant use in both electronic or electrical applications and in the world of engineering. That's why obviously they are also being improved aggressively with respect to time. Okay, so a capacitor can hold any amount of energy from an ample level to a juggernaut magnitude. Juggernaut means very huge force, no, or very huge quantity. So from an ample level to a juggernaut magnitude, we have to use it properly. Who knows what the future holds for us with them? So imagine that a capacitor resisting any change in voltage and capable of storing and discharging these collected charges. Then if we can only have the wisdom of strategically using them, then I think we can go further with the improvement of our technology because we are um, processing these stored charges. No, so I think you are with me with that concept. So now here comes the question: if you try to compare a capacitor to a battery, or what, like they will clash with each other, which one is better? Are they similar? Are they equal? Are they different? Or which is better, or which is more significant? Batteries or capacitors? Okay. So what would be the answer for that? The batteries or the capacitors? Okay. I'll give you some time. Battery or capacitor? So let's proceed. When you compare a battery and a capacitor, both store electrical energy. Both have two terminals. But a battery is a transducer. Inside it, chemical reaction produce electrons on one terminal and absorb electrons on the other terminal. Unlike a battery, a capacitor does not create electrons or charge. It only stores them. So, no? So I hope you can now see the difference between a battery and a capacitor. Now, the difference between a capacitor and a battery is that a capacitor can dump its entire charge in a tiny fraction of a second, where a battery would take minutes to completely discharge. No, so in terms of discharging speed, capacitors are very fast when compared to the discharge time of a battery. That's why they are used in photography, like flash photography, no? And the electronic flash on a camera uses a capacitor. The battery charges up the flash's capacitor over several seconds, and then the capacitor dumps the full charge into the flash tube almost instantly. Okay, so as you can see, the flash in our cameras, no, that's the sudden dumping of charges by the capacitor, in which batteries are unable to do. No, and also all about our flash drives or our flash memory. Flash memory is all about capacitance. It's not about batteries. It's all about capacitance. Okay, so I think it is in this part, the discharging time, speed, and flash memory, it's all about capacitance, and it's not about batteries. But of course, they have to work hand in hand, no? Because as we know, these devices, electronic devices, we cannot use the camera without the battery, no? And we cannot use some appliances, some gadgets without battery. So obviously, the battery will provide the power, but in terms of processing this, some charges for camera flash and for memories of our flash drives, it's all about capacitance. Okay, so I think there's no such thing as that battery is better than capacitors or capacitors are better than battery. They just have different roles in terms of application, both in electronic and electrical applications. Okay, so a large charge capacitor is extremely dangerous. Take note, no? So that's why if you see a capacitor, do not hold it directly, especially the terminals, because your hands might serve as a conductor to discharge the charges within the capacitor, and you will be electrocuted with that, no? And that's very dangerous. So that's why you have to use if you see a capacitor, use a screwdriver and discharge it first before holding it with your hands in order to protect yourselves, no? Flash units and TVs have warnings about not opening them up for this reason. They contain big capacitors, especially those monitors or televisions that are CRT, cathode ray tube TVs or monitors. They have very big capacitors inside them. So please do not hold them directly. Please protect yourselves. Discharge them first because that can potentially kill you with the charge they contain. Again, discharge a capacitor before holding it. Okay. So, so, so if you have these conductive plates, no, this is just a review, no, with the slide earlier. There in a capacitor, there are two conductive plates and a dielectric. It's like a sandwich. It's like a sandwich, and the blue one is the spread, no. And this conductive plate is separated by a specific distance. So you can easily make a capacitor from two pieces of aluminum foil and a piece of paper. It won't be particularly a good capacitor in terms of its storage capacity, but it will work. No, so just you put two, let's say two copper sheets and then a paper in between them. That's already a version of a capacitor. No, so that's if you just have two conductive plates and an insulator between them, that is already a version of a capacitor. Now, speaking about dielectric, no, we have to see a clue. So in theory, the dielectric can be any non-conductive substance. However, for practical applications, specific materials are used that best suit the capacitor's functions. The dielectric dictates what kind of capacitor it is and for what it is best suited. Now, most capacitors are named for their dielectric. So if you hear the word paper capacitor, clay capacitor, ceramic capacitor, glass capacitor, mica capacitor, air, mylar, tantalum, film, vacuum, etc. So a capacitor is named usually with the dielectric inside it. No, so if your capacitor is using a clay as a dielectric, then call it clay capacitor. If it's using ceramic as its dielectric, then those are called ceramic capacitors. No, so that's how important that we determine what is the dielectric of any given capacitor in order also for us to know what is the name of that capacitor. So depending on the size and type of dielectric, some capacitors are better for high frequency uses while some are better for high voltage applications. That capacitors can be manufactured to serve any purpose from the smallest plastic capacitor in your calculator to an ultra capacitor that can power a commuter bus. So see, so with this, we have small charges and very high charges, very huge amount of charges. So there are various applications, strategic applications of how we sample, how we manage, how we strategically apply these charges, charge, discharge. Imagine the application, no? So that's why capacitors are extensively used in the world of engineering, no? So in terms of total capacitance calculation, if you connect the capacitors in parallel, like for example, we have C1, C2, C3, and C4, you simply add them. The total capacitance for this, you just add C1, C2, C3, and C4, and so on. If you add further capacitors in terms of parallel connection. But if you connect them in series, like this part, the total capacitance is 1 over the summation of the reciprocals of all the capacitors. No, if you recall the total resistance calculations, no, when using capacitors, it's the opposite for capacitors. No, so this is the total capacitance calculation whenever capacitors are connected in parallel or connected in series. Now, there are different types of capacitors and with varying levels of applications based on their unique characteristics and capabilities. No, we have small capacitors, flat capacitors. We have like cylinders. We have different colors. We have like it's like a plastic. It's a mica. It's a mylar. There are several kinds of capacitors depending again of the applications. So As you can see here, we have film capacitors, variable capacitors. So I'm just presenting you here, no, their appearances: tuning capacitors, polyester film capacitors, ceramic, electrolytic, polystyrene, trimmer, and we also have ceramic, monolithic, deep silver mica, mylar, no, tantalum, radial aluminum, axial, ceramic. Then we have the trimmer, tin. There are actually very different. They're very um, they're very assorted. They are very dynamic in terms of application. No? So these are the capacitors. Maybe if you will go to an electronic store to buy some, I think if it is your first time, you will be surprised like, oh, capacitors have different forms, different types, different colors, different values, different applications. That's how widely capacitors are used in the electronics and electrical engineering industry. No, so that's why we have to also to have an ample or full knowledge of how these components are being used. No, especially their characteristics and how to handle them with safety. So the most popular and commonly used capacitors are the electrolytic capacitors, no? Electrolytic, or those with electrolytic means polarized capacitors, no? That means that they have a positive terminal and they also have a negative terminal. And usually their form is like a cylinder, cylinder. As you can see here, these are examples of electrolytic capacitors, and also these are also electrolytic capacitors. And uh, I hope this tape measure will also give us the idea like how large or how small they are, And this is a motherboard. You can also see this like cylindrical figures. These are polarized electrolytic capacitors. They are also mostly used in terms of creating computers. Now, as you can see, these are the external details of an electrolytic capacitor. As you can see here, this is the manufacturer's name. Let's say example, this is a Rubicon. The maximum voltage, that means 400 volts. It can handle 400 volts in terms of storing, no? And the capacitor value is 150 microfarad. So in terms of polarity, if you look at the capacitor, the one with the strip is the negative terminal, and the one with no strip is the positive terminal. You can also see here the maximum temperature before the capacitor will melt or explode. It can keep up operating even if it's already 105 degrees Celsius, no? And we have the capacitor series. This capacitor is series CE, no? And if you can also see the tantalum capacitor, the positive sign is the one in line with this marking, no? So this is the positive sign, and this is the positive lead. That's for tantalum capacitor. Okay, so I hope when you hold or when you look at the mostly used capacitors, the electrolytic ones, you can be guided as to where the negative terminal is, and you can also know how also know how to read these details. Okay, so proceeding, what is inside an electrolytic capacitor? If you open it, this is the thing that you will see, no? This is the negative charge connection, the positive charge connection, and the dielectric, the metal plate, the aluminum and plastic insulation. These are like being cut across, and we see the different layers inside the commonly used capacitor, the electrolytic capacitor. So at least we already have an idea what is inside these capacitors. Now, what is inside a ceramic capacitor? So these are ceramic capacitors, no? You can see a protective coating here, a ceramic disc, that is the dielectric. Okay, so ceramic disc, that means ceramic disc is the dielectric. These are called ceramic capacitor because the dielectric is a ceramic material, no? Then we have this electrode as the plate, and we have these connecting wires indicating their terminals. And as you can also see here, there is a hold-off kink. What we see here is a kink. Like interestingly, why not just create a straight line? Why create a somewhat like curve design about this? So if you look into it and do further research, the manufacturers realize that creating a kink, like a small curve, instead of just creating a straight line, the kink actually reinforces the capacitor not to be broken easily. no, in terms of handling. So the hold-off kink is a strategic geometrical design in order to not break easily the terminals of the capacitor. No, so that is the purpose of this kink. No, so that's why it's if you see ceramic capacitors, you can usually see some curves. So again, the purpose there is to reinforce significantly so that these terminals will not be easily broken in terms of handling. Okay, so when checking a good and a bad capacitor in a circuit board, how will we know by visual inspection, no, whether it's a good capacitor or it's a bad capacitor? So there are some terms about the bad thing that we need to consider. So it's bad, possibly bad, when you notice any of these three visible signs. If you see a crack or break, no? So if you look in this picture, if you see some certain cracks, that is already a bad capacitor. If you see bulging or bloating or like it's like somewhat, if you see it visually, it's like about to burst or like fatter, no, I'll just use the word fatter than the traditional size. That's bulging or bloating, no, and the rusting, no, due to some moisture and oxidation. Those are already guides for us to know that, oh, these capacitors needs to be replaced with new ones, because in terms of performance, they may not be delivering the performance or the farad or the expectations that are expected from them. No, so if you see cracks, bulging or rusting of capacitors, then as much as possible, replace them the soonest possible time. Okay, so like for example, this is a row of failed capacitors with bulging tops. Now they are already bulging, and a row of good capacitors with flat tops. No, so again, a good capacitor had flat top, but the bulging ones are already considered as bad capacitors. How about this one? It's bulging, it has a crack, and it already has rust. No, also this one already bulging. This one, these ones have cracks. So please, the soonest possible time, replace these capacitors in order to keep the circuit in operating efficiently and effectively. Okay, so at least, again, we are always reminded that there are visual signs to check whether a capacitor is still good or already in bad condition. Now, what are the significant applications of capacitors in our world today? No? So let me discuss to you. What are the significant applications of capacitors in our world today? So we have this, no? We have several overlapping applications of capacitors. Like for example, we have the ceramic capacitors group, the film capacitors group, and the aluminum electrolytic capacitors group, no? So let's proceed to the next slide to see those very important applications of capacitors that we've been already using or about to use in our daily lives. So these are energy storage, pulse power and weapons, power conditioning, suppression and coupling, motor starters, signal processing, sensing, oscillators, hazards, and safety. Okay, so let's start with energy storage, no? So a capacitor can store electrical energy when it is connected to its charging circuit. And when it is disconnected from its charging circuit, it can dissipate that stored energy so it can be used like a temporary battery, no? So that is the primary side effect of the function of a capacitor. Since it resists any change in voltage, then it is capable of storing and discharging electrical energy. In order to keep the circuit it is being connected to operating. Okay? So the first application of capacitors are energy storage. No? The second one is pulsed power and weapons, no? So what I'm presenting here to you is a Marx generator. We have the 10 kilovolt battery here connected to a parallel connection of the capacitor. So, di ba, if you connect capacitors in parallel, that means you are adding their value. And then you might also discharge them in series. This is what you see. This is the Marx generator. No, this arcing here is the discharging of capacitors. So visually, you can see that is the effect of when designing Marx generator circuit. No, and these are inspirations in creating pulse power and weapons. No, so groups of large, especially constructed low inductance, high voltage capacitors, or sometimes called as capacitor banks, are used to supply huge pulses of current. No, so these are huge pulses of current or arcing. Sometimes it's called arcing, and inspiration for many pulse power applications. Okay, so they can be used for nuclear weapons, lasers or light amplification by stimulated emission of radiation, lasers, fusion research, and particle accelerators. So wow, those are the those are the high high level applications, no, of the capacitors. No, they can be used in weaponry, and they can be used for research and accelerating particle movements. That's how wide the use of capacitors is in the engineering or science industry. No, hopefully that time will not come that these pulse power weapons will be used among countries, no, because that might signify the end of the world if the nuclear weapons and lasers will be used further, no. So let's all pray that that will not happen, that these weapons being improvised and created with the use of with the strategic use of capacitors. Let us hope that that will not happen, that this will be used among all countries in the world, no. You might even see it in the games, no, but this pulse power and weapons, they are technically always experimental work. They're underway using banks of capacitors as power sources, like for example the electromagnetic armor and electromagnetic railguns or coil guns. So maybe you can see them in the games, you can see them in the movies, but maybe as of now, like as we are talking, these weapons are already being created by some first world countries, no, and they are just being maybe secret about it, no, because obviously it's not always a norm that a country will share its high tech weaponry or advanced levels of weapon development and share it to the world. Most likely they just keep it to themselves, no. So as much as possible, again, we look forward that there will no longer be world war that might happen in the future, because that would be very scary thing to think, no. So again, just just keeping ourselves objective, capacitors are widely used in the development of these weapons and pulse power systems. Okay, the next use of capacitors are power conditioning, no? So capacitors are connected in parallel with the power circuits of most electronic devices and larger systems, such as factories, no, to shunt away and conceal current fluctuations from the primary power source to provide a clean power supply for signal or control circuits, no. We are all using power, and with these control circuits, they are using capacitor in order to smoothen out, manage, and regulate the transmission of these powers, no, especially to the end areas where this power will be used, no, to household communities, to companies, and to factories. Capacitors are used with that. Now, so we have the power factor correction because three capacitors, let's say VAR, connected as three-phase load to counteract inductive loading. Because capacitors, it's the nemesis of capacitors, or I'll just use the word nemesis, no, because in terms of power factor correction, if if the total circuit's behavior is more inductive and you want to suppress that, you have to add more capacitors in order to suppress it being inductive. And if the total circuit is more capacitive, that means you have to add inductors in order to remove for it being more capacitive in order to neutralize. So technically, by design, capacitors and inductors, in terms of power factor correction, they are neutralizing each other. Again, if it's more capacitive, if you want to remove it being more capacitive, put inductor. If you want to remove it being more inductive, put capacitor, no? In that's it. In terms of electric motors and transmission lines, in order to make the load appear to be mostly resistive. Because in terms of power factor, mathematically, the real part is the resistive part or the resistance, and the imaginary part can either be capacitive or inductive. So in order to perform maximum power transfer, the load should be totally resistive. So that's why you have to cancel out capacitiveness or capacitive reactance, or you also have to cancel out inductive reactance in order to make the circuit purely resistive and maximum power transfer will happen. No, so that's in terms of power conditioning. Again, the use of capacitors also with inductors are used, no, to smoothen out and improve the delivery and the operation of power conditioning. Okay, now they are also used in suppression and coupling. So a capacitor connected in series with the load to be coupled, no, is different in terms of a capacitor connected to the load in terms of series and parallel. If it is connected in series, that means it allows AC signal and blocks DC signal. But if it is connected in parallel manner with respect to load, it allows DC signal and it suppresses or cancels out AC signal. No, so as what you can see here, if one circuit is connected to another circuit with the connection of a capacitor being connected in this manner, it allows AC signal from circuit 1 to pass to circuit 2. But if this capacitor is connected in parallel, otherwise, it will allow DC signal and it will reject AC signal. No, so that is the use of coupling and decoupling of capacitors. As you can see here, this is an example of a cascaded instructor transistor connection. No, like this is stage 1 and this is stage 2. So the C2 here used is coupling. C2 here, C1, C2, and C3 here are counted off as coupling capacitors. No, it's called capacitor uses capacitive coupling or AC coupling because it allows AC signal to transfer from one part of the circuit into another, no, or connect one stage of a circuit to another stage of a circuit. So this is what you call coupling. But if you connect it otherwise in a parallel manner, that's called decoupling because it will not allow AC to enter from this part of the circuit to the next part of the circuit, but it will allow DC. No, so that's how interesting the capacitor is in terms of its connection to the load. It behaves differently if you connect it in parallel, and it also behaves differently if you connect it in series. Okay, so let's proceed. No, like for example, this is an AC signal here. We have the low pass filter and the high pass filter. Now the low pass filter, so as you can see visually, it involves one resistor, one capacitor, one resistor, one capacitor. Now if this is the load part now or the output part, if the capacitor is connected, no, parallel to the load, it's called low pass filter. But if the capacitor is connected in series to the load, it's called high pass filter. Okay, so it's just the orientation. If it's a low pass filter, that means if it will allow low frequency signals to pass and it will cut or reject high frequency signals. Now, in terms of high pass filter, it's the opposite. It will reject low frequency signals, but it will allow or it will pass the high frequency signal. Again, the difference between low pass filter and the high pass filter is the orientation between the resistor and the capacitor with respect to the load. No, so that's why we have the low pass filter, high pass filter, band pass filter, and band reject filters. No, band pass filter and band reject filters is that These are just created with a combination of a low pass filter and a high pass filter. It depends on the prioritization on the output side. Now, we now go to the RC snubbers, no, on the suppression and coupling. A simple snubber uses a small resistor in series with a small capacitor. This combination can be used to suppress the rapid rise in voltage across any sensitive electronic component. So what do you mean by that? If this is this is across the load and across the contact, like for example here, we know, or as we know, the magnetization or the current inside any given coil can be very dangerous when being channeled suddenly to any part of the circuit. So in order to protect that, if in case that this will be channeled suddenly to any part of the circuit, we need to put a capacitor. No, we need to put a capacitor in order to protect the other parts of the circuit. Like for example, since capacitors are main purpose is to resist any change in voltage, and when this sudden voltage coming from an inductor in the form of current will be channeled in the other part of the circuits, then the capacitor will absorb that. No, will absorb that rather than the sudden spike will go to the other part of the circuits. At least the capacitor will save the circuit by absorbing totally those excessive or extra voltages. So this is very, very significant, especially if your circuit involves sensitive components like transistors, like integrated circuits or ICs. No, so you have to use capacitors in order again to counteract any change in voltage, because any change in voltage might destroy specific components, specifically those very sensitive ones. No, so the term here is snubbing. Snubbing, no, snubbing. Now, we now also have the use of capacitors as motor starters. What do you mean as motor starters? Some motors cannot start without an aid of a capacitor, no? Without an aid of a capacitor. So if you can read here, you can see a motor cap, no? Motor cap or motor starting capacitor, because these motors needs primary the term there is like a primary current, no? Primary current or starting current in order for them to start up and function. Even though because we have these motors, if they have current rating, it doesn't mean that if we just supply that current rating, automatically the motor will work, no? In a normal level, uh, even motors, sometimes you have to multiply it by 5 or multiply it by 8 their current ratings just to make them start or to turn them on for the first few minutes, no? So that's why we need motor starting capacitors to help them to jump start and start operating, no? So motor starting capacitors are typically non-polarized electrolytic types, while running capacitors are conventional paper or plastic film dielectric types. Again, the purpose here, no, is a capacitor starter motor has a capacitor in series with a starter winding, no? So these are connected to these motors just to make these motors start in terms of operation, no? That's how significant the capacitors are, because there are many type of motors that doesn't start automatically unless you put a very um, huge amount of voltage or startup current in order for them to really turn on and start working. So that's where the capacitors come into play. Okay, so in terms of signal processing, no, we have CCD or charge coupled device. Capacitance is also used in this design, no? In terms of information representation, the energy stored in a capacitor can be used to represent information, either in binary form, as in DRAMs, or in analog form. No, I think I have also discussed this earlier that even flash memory uses capacitance. So how much more about these charge coupled devices, no? In our motherboards, in our computers, in our different electronic circuitries involving the use of sensors, involving the use of actuators, involving the use of transistors, integrated circuits. Capacitance play a major role, no? In the form of representing this energy storage in the form of information, no? Like DRAMs or dynamic random access memory, no? So you have to put that in mind. Capacitance is widely used in signal processing, no? Like for example, as you can see here, no? This is a tank circuit, no? As you know, this tank circuit is the core circuit. That's why when we change the station, when we change the station of the radio station we are listening, it's all about this formula, no? The tank circuit. The tank circuit is a parallel of the parallel connection of a capacitor and an inductor, and we have this formula, the resonant frequency, like 1 over 2 pi square root of LC, no? So if you obviously with this setup, you cannot, there's no such thing as variable inductor, because this is physically the number of coils or the number of turns and the length, that already serve as guide of what is the inductance value. But the capacitor, we use a variable capacitor in order to change the value of the frequency, no? Because 1 is constant, 2 is constant, pi is constant, then L is constant, but this value of C, since we are using a variable capacitor, we can alter this value. That's why as you change the using your radio, no, as you turn this knob, you're actually changing the value of the capacitor. No, and if you change the value of the capacitor, the frequency will also change. Like for example, if you're listening to an FM of 99.1, no, so that's the frequency, 99.1 megahertz, and then suddenly you want it to go to 96.7 megahertz or FM station, then you notice you turn this dial. Actually, this is what you are seeing by your naked eyes. But what's happening in the equation is that you're actually changing the value of the capacitance. That's why the radio changes its reception to the expected frequency. FM station, you want to change the station, that's changing the result of changing the capacitance, no? So this is a strategic use of capacitor paired with an inductor, no, in signal processing. I hope you now know that turning this dial or changing like FM station or the AM station in your respective radios, you're actually altering the capacitance of the LC circuit or the tank circuit, sometimes called tuned circuit, LC circuits, or tank circuits, no? It is used in radio receivers to select or tune to the desired station frequency, no? Now, by varying also the dielectric, I hope you are familiar with this. These are humidifiers. These are using the concept of capacitors or capacitance, no? In terms of sensing process. The effects of varying the characteristics of the dielectric, plate area, and plate distance can also be used for sensing and measurement. So these are used in the humidifiers. Now, I think some of you have this in your home, or some of you have not. But again, if you see a humidifier, please take note that it is using capacitance in terms of its functionality. Okay? How about, again, the use also of sensing process? The use of biometrics. No, the use of biometrics, no, like we use our hands, we use our eyes, no, in order to confirm our identity, or even the adjustment of our voice, no, like you filter your voice. Capacitance are used, no, to enhance voice quality. There are special circuits where capacitors are massively used with that, no. So these are some examples again of signal processing utilizing capacitance. How about also, no, smartphones, the tilt sensors in our phones, no, like we do the tilting of our cell phones, and even the pressing of apps, the way we swipe the screen of our smart cell phones, those are all about capacitance, no? Now, the effect of varying the characteristics of the dielectric, plate area, and plate distance can also be used for sensing and measurement. So when you play games with your touch screen smartphones, it's all about capacitance, no? And even the tilt sensors, like we do the 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 gestures of our hands, those are all about capacitance. Okay, and we also have oscillators. No, oscillators is as an oscillator is a special type of electronic circuit capable of generating pulses. So as you can see, this is an op amp, a symbol, this triangle here with a plus and minus sign. This is an op amp connected. Like for example, this is called the Hartley oscillator, no, because it uses two inductors and one capacitor. With this setup, it is capable of generating an AC signal to a specific frequency. So again, capacitors are used in order to create oscillators. No? Next, hazards and safety. No, monitoring the fuel level on commercial airplanes and space vehicles. Again, they are using capacitors. No, capacitors are proactively used to provide safety to industrial plants and common vehicles used by people. So even in this aerospace applications and airplanes, capacitors again are used. Again, that's if you just know how to manage the charging and discharging and connecting capacitors in series or parallel, there are many uses, no? Like imagination or sky is the limit if you'll just know how to design them. But again, always think about safety, no? Because these charges, when being mishandled by you, might electrocute you in the process or might create accidents. Okay. Now, so these are used also in industrial plants, no, industrial plants and other factories. Now, there's also this automatic inflation of airbags on land vehicles. So if you have a car and suddenly there's a design that if you bump into something or if there is an accident, automatically these airbags will inflate to protect the riders or the people inside the car. Again, this concept focuses more on using again capacitors, using their charges to create instant supply of voltage to activate actuators or sensors for the purpose of safety and to protect lives in terms of application. Okay, so those are several examples of the use of capacitors, no? So with that, let us always put into mind that capacitors capable of charging and discharging with its main purpose of resisting change in voltage level in any given circuit it is being connected. There are different applications, significant applications that it is being used to, being paired with other electronic components, resistors, being paired with diodes, being paired with ICs, op amps. Then that's how important, no, capacitors is. Capacitors are in our lives, no. So I have presented to you the applications. Now let's now proceed to some relevant terms for capacitors. No, these are the relevant terms for some capacitors. Let us be oriented about these terms because these terms we might encounter this also with other major subjects we have in let's say in computer engineering, in mechanical engineering, electrical engineering, electronics engineering, or physics, sciences. We have to take note that we are to be familiarizing ourselves with these terminologies because if we have an orientation or we are familiar about their definitions, then understanding further concepts about where they are used again, it will be easier for us to do that, no? Like for example, permittivity. Permittivity is a measure of how well a dielectric will permit the establishment of flux lines within the dielectric. Electric flux lines means the lines. Now, these are the lines drawn to indicate the strength and direction of an electric field. The dielectric, by definition, is the insulating material between the plates of a capacitor. Dielectric constant or relative permittivity is the permittivity of a material compared to that of air. Electric field strength is the force acting on a unit positive charge in the region of interest. And the breakdown voltage or dielectric strength is an indication for unit length to establish conduction in a dielectric. So 1, 2, 3, 4, 5, 6. I have 6, 7, 8. I have 8 new terminologies here. So as much as possible, if you have extra time, try to research, no, what are these terminologies so that you can understand better how they are connected with the concept of capacitance and with the concept of electricity, with the concept of electronics engineering application, or in your research or in your sciences, try to explore further what does these relevant terms connected to capacitance are. Okay, so proceeding, we also have surge voltage. Surge voltage is defined as the maximum voltage that can be applied across the capacitor for very short period of time. Working voltage is the voltage that can be applied across a capacitor for long periods of time without the concern for dielectric breakdown. Stray capacitance is the capacitance that exists between two conducting surfaces which are relatively close to each other. Time constant, or is the required time for the charging and discharging phases of a capacitor. No, so in terms of analysis, that because capacitors also have this characteristic curve, no, you always look for the time constant, no, and about the charging and discharging phase, we usually use the term time constant for that. Okay, and we also have the term leakage current. No, the leakage current is the resulting current created if a capacitor is disconnected from the charging network for a sufficient length of time. And fringing. Fringing is an effect established by flux lines that do not pass directly from one conducting surface to another. So again, no, another 1, 2, 3, 4, 5, 6, another 6 new terms, or maybe you have encountered some of these terms already in your learning, or during studying. No, so again, if we want to appreciate more these terminologies, we need to be familiar about their definitions and how these terminologies are connected to each other. No, like for example, with these some relevant terms for capacitors, we have this one: permittivity, electric flux lines, dielectric constant, electric field strength, breakdown voltage, and we also have the surge voltage, working voltage, stray capacitance, time constant, leakage current, fringing. These are all connected to each other, no? So we just need to contextually study their connection in order for us to understand better, rather than simply memorizing their definitions, but without knowing why are we memorizing them in the first place, no? So these are terminologies that needs to be connected to each other in order for us to appreciate better the capacitors and its important applications and its key characteristics, no? So that will give us aha moments, and that will also give us new discoveries, no? Like with this vast application of capacitors, from energy storage, from the applications in our cell phones, from the applications with the safety in the workplace, in the factories, in the manufacturing plants, in the airspace, no? Even in the use of our cars, no? Even in the use of weapons, these capacitors are very significant to deal with. Since again, we are dealing with stored energy and energy that can be discharged instantly with a very fast discharge time. This needs prudence in terms of understanding. This needs safety, and this needs interconnection of knowledge of some terminologies that we might already have encountered with our previous electronics subject, or previous electrical subject, or science subject, physics, chemistry. That's how widely encompassing the capacitors are, no? So again, whenever you encounter some terminologies, new terminologies, please try to research further about these terms in order for you to understand better also how capacitors work. Okay? So now it's time for us to proceed to inductors. No, inductors are these are sample of inductors, or just coils, no, coils of wire being being connected or being created to some lengths, to some diameters, no? So we have here Joseph Henry and a picture of some inductors, but now we have to define first the inductors, no? Or what is an inductor? So an inductor is a fundamental element of electrical system constructed of numerous turns of wires around a ferromagnetic or air core, no? So this is just a simple wires being constructed in a numerous number of turn, no? No, so if the primary function of the capacitors is that it resists any change in voltage, then the primary function of inductors are that it react or resist any change in current, no? So if capacitors resist any change in voltage, inductors resist any change in current, no? And the side effect of that, if the side effect of resisting voltage of capacitors, the side effect is that it can either charge or discharge. For the inductors, because of their reaction or their resistance in any change in current, they are then capable of generating a voltage in opposition to the applied voltage and proportional to the rate of change of the current, no? So it is impossible to change the current through an inductor instantly, no? So as any such change would produce an infinite voltage, no? So the unit for inductance is Henry, in honor of Joseph Henry, because among all scientists, in terms of, if we go back to history, it was Joseph Henry who have made significant study, significant remarks about the use of inductors. So in honor of him, the unit for inductance is Henry. Okay, so these are the various types of inductors. Okay, these are the various types of inductors. No, so typically they are just coils. No, being mutually connected to each other, being turned in a certain core. So these are the various types of inductors. I think you can see them differ in terms of length, in terms of diameter, and in terms of their geometrical construction. Okay, so I hope we familiarize ourselves with these various types of inductors. Now proceeding, this is again an analogy of what is the main function of inductor, of any inductors, no? If there is a change in current, the inductor will resist the change in current, no? And with that, sometimes an inductor is also called as choke, no? As you remember, the first name of capacitors are known as condenser. But on the side also of inductors, an inductor, because of its behavior of resisting any change in current, they are sometimes called as choke, no, like choking the current if there's any change, no? So self-inductance or inductance is defined as a measure of the ability of a coil, obviously, the inductor is a coil, to oppose any change in current through the coil and to store energy in the form of a magnetic field, no? So with the resistance of capacitors to any change in voltage, they store electrical energy, no? They store charge. But in the context of inductors, they store energy in the form of magnetic field, no? So in the region surrounding the coil, it is measured then in terms of its unit, Henry. Okay? So if the capacitor stores energy in the form of charge, the inductors store energy in the form of magnetic field. Okay? So proceeding, if this is the definition for self-inductance, we also have a definition for mutual inductance. Mutual inductance is a measure of the amount of inductive coupling that exists between two coils. So if this is one coil and this is the second coil, let's say this is the primary winding and this is the secondary winding, if you mix them all together, connect them with this fashion, it's called mutual inductance, or mutual inductance happens between these coils, no? And one very good example for that is the transformer, no? That's why this is called the primary winding being mixed with the secondary winding, and this is the core. The core is a ferrite material. Ferrite means it has a component of iron in it in order to further enhance the magnetic capability of the coils. And one very good example of this connection is the transformer, no? So the transformer is one good example of an electrical device or component utilizing mutual inductance. Okay, so and then as we know, transformers are capable of stepping up or stepping down the voltage. Like for example, in our households during the power transmissions, no, as you can see in the poles, in the electrical poles, those big cylinders, those are the transformers, no? Since during the transmission, these are high voltage transmission, but what we are using in our households are only 220 volts, no, AC, and then we need to translate that into DC. So this kilovolts transmission is being stepped down using these transformers, no. So basically these are step down transformers, and then they channel it to our households, and then we can get the power then in our electrical outlets, no. But those are in AC form, and of course we need to use rectifiers within our appliances or within our devices in order to use the AC into usable DC, no. So thank you to the transformers, because transformers are being created with the use of mutual inductance between two coils, the primary winding and the secondary winding, within a ferrite core. Okay? So in terms of series connection, if you connect in this fashion the inductors, the total inductance would be, you simply add L1, L2, and L3. That is how you calculate the total inductance. No? So I think this is similar to the adding total resistance, no, when you deal with resistors. Okay? So this is to get the total inductance if you do a series connection. But if you do a parallel connection, the formula would be 1 over the summation of the reciprocals of L1, L2, and L3. So again, this is the formula to get the total inductance. Again, it is very much similar to that of resistors, no, in getting the total resistance if you do a parallel connection. So I think in terms of parallel connection and series connection, the resistor and the inductor is the same, but it's the opposite for the capacitors, because it is the reverse, no, it is the reverse of the idea. So some relevant terms for inductors. Again, we're dealing with inductance. Earlier, we have discussed several terms about capacitance. There are also other terms that we also need to orient ourselves again, or be oriented if these are new to us, about inductance, or some terms for inductors. And these are, first is Faraday's law. Faraday's law is a law relating the voltage induced across a coil to the number of turns in the coil and the rate at which the flux linking the coil is changing. Then we also have choke. Choke is a term often applied to an inductor due to its ability to resist change in current through it. Then we also have Lenz's law. Lenz's law is a law stating that the induced effect is always such as to oppose any change in the current through the coil and to store energy in the form of magnetic field in the region surrounding the coil. No, so we have here Faraday's law, choke, and Lenz's law. Again, no, if we want to further amplify our learning about these laws and about these terminologies, you can always do further research, no, and read other learning materials in order to enhance our reinforcement in learning inductors and the concept of inductance, no. So these are some formulas that you might need to be familiar with, because if you want to solve for the voltage across, like we have this resistor, the capacitor, and the inductor, no. So if you want to solve the voltage across any given resistor, you simply have to use V equals IR. So I think this formula is derived from Ohm's law. So V equals IR. But for capacitor, the voltage across any given capacitor is equal to 1 over C integral of I with respect to dt. Okay? With time. And in order to solve also for the voltage across the inductor, that is simply equal to L. L here is the inductance or the inductor's value multiplied by the derivative of current with respect to time, L di dt. Okay? For the current flowing for the resistor, that we use the Ohm's law, no? I equals V over R. But for the capacitor, in order to solve for the current, it's equal to psi dV over dt, no? Or the derivative of voltage with respect to time. And in order also to solve for the current flowing in an inductor, it is equal to 1 over L times integral of voltage with respect to time. Okay? In terms of energy storage, there are no formula for resistor because it's a passive device, no? It's a passive device. So uh, when you say that it is a positive device, that means it is not capable of creating its energy or storing its energy, no? In which the capacitor and the inductor, they are capable. That's why they have formulas, no? So the formula for that, for capacitor, is it is equal to 1/2 times CV squared, and for the inductor, it's 1/2 times Li squared. So again, no, these are formulas that you need to familiarize yourself with, especially on analyzing circuits in simulation, in order to understand better how a given circuit works, especially if it involves resistors, capacitors, and inductors. No, maybe sooner you will be analyzing RLC circuits. No, they use the term RLC circuits, or circuits that has resistor R, L, inductor, and C. No, so it would be very beneficial for you if you try to familiarize and do some problem solving drills if you have some time, in order again to appreciate and understand better how to design circuits involving resistors, capacitors, and inductors. Okay, so that is all, folks. I hope you have learned some of my discussion about capacitors and inductors. Okay, this is Engineer Lojan Bistampa, and thank you so much for listening. God bless us all.